Okay, let's get started. Um, it's a little bit empty here today, especially this side of the room. Must be a final exam or project due or something. Any questions or comments? Okay, and just wanted to reiterate that this is actually the last lecture, so there is no lecture on Tuesday. So hopefully we'll finish up all the material today. As you guys know, the project is due on the next lecture, basically, which is not a lecture, on Tuesday. Last time when I said you guys could get together and chat about it, I didn't quite realize that that was also the due date. So it doesn't make sense to make changes on Tuesday. Sorry about that. You guys were laughing, but nobody said anything. So, okay. It was a good joke, even though I didn't realize it. Oh yeah, for the project. So as you know, you're going to email me the project report, one per group, and also email me a separate attachment with just your net list, basically. So I should be able to take your net list and run it in Spectre and verify your results. Now, I don't plan to do that for everybody, so I have better things to do. But, and I do trust you guys, so I apologize ahead of time for requiring you to do this. But there's two reasons why I want to see your net list. One, if the results are a little suspicious, if they look like they're too good to be true, definitely I'll run them to make sure that they are true. And if it's something very interesting that I haven't seen before, I like to play around with it and see how it works. So those are the two reasons, just to let you know. Anything else? And then just to remind you guys about the final exam. So there are no office hours today, no office hours next week. Monday I will hold special office hours from 1 to 3. So let me write that down for you guys. So Monday, I believe, which is going to be the 15th, 1 to 3 p.m. And please don't be shy. If you need to reach me in between now and Monday, send me email and I'll be happy to answer your questions. Okay.
Short question. Is there a way that we get back the remaining homeworks before the exam?
Yeah, that's a good note to self. So maybe what I'll do is I'll ask the reader to come in on Tuesday with all the homework material and return it. Yes.
Post the reports from project reports on the website.
If there are no objections, yeah, I'd be happy to post them. Yeah. So if someone doesn't want their project posted, let me know. One issue is, of course, future generations of students. And the nice thing is that when they're doing the project, it's cool to be able to look to see what other people have done and try to improve upon that. At the same time, designing amplifiers, there's only so much you can do. So if someone gets a hold of your project report, they can probably reproduce your results pretty quickly and get the project done. Well, that's their loss, really. Okay. Anything else? All right, so let's get back to where we left off. As you'll remember, we were talking about charge injection. And let me just remind you of what we mean by charge injection. So the idea is we have a transistor. It's acting like a switch. It's connected to a capacitor, our sampling capacitor. On one side, it's connected to the input. And when the switch is on, the input charges up this capacitor to the right value. But the problem is when we turn the switch off, the channel charge basically has to go somewhere, right? For this transistor to actually turn off, we have to discharge this gate to channel capacitance. And in that process, some of the charge leaves this junction, which may be the drain or source, and some also leaves through this junction. So what we end up getting is some delta V here, which is due to charge injection. And this, remember, has nothing to do with the overlap capacitances. This is an independent source of error. So even if we had a transistor with very low overlap, we still would get charge injection from the intrinsic charge in the transistor. Okay. Now, one of the questions is, how do we actually figure out where this charge goes? And as we discussed last lecture, it turns out with a lump circuit, there's no way to know. And that's for that reason even SPICE doesn't actually calculate this charge injection correctly. We can just actually jump ahead and talk a little bit about that. So it turns out in SPICE, there is a parameter called XPart. And part stands for partition. So this is the charge partition parameter. And in the old days of SPICE, the charge partition was 0, 100. In other words, 0% of this channel charge would go to source and 100% would go to drain. Now this is of course completely arbitrary because it turns out that, first of all, what's the source, what's the drain, right? That's kind of meaningless. Also, this charge partition doesn't even satisfy the current continuity equation. So this leads to charge non-conservation. I mean, it's got all sorts of problems. So 0, 100 is actually a very bad choice. People like it because the waveforms you get at a 0, 100 charge partition kind of look physical. You don't get undershooting. Anyhow, you could read more about it if you're interested. But it's a very unphysical charge partition, but you might find that in a lot of compact models, this is in fact the default charge partition, 0, 100. Kind of works well for digital circuits and people just keep it. Make sure that you're aware of this problem. When you're working very seriously with circuits that deal with charge, look to see what your model is selected. Nowadays, fortunately, the default, unless someone changes it, is 4060 charge partition. And 4060 charge partition turns out to be the most physical charge partition that you can have. It satisfies the continuity equation. And intuitively, if you think about it, there's more charge near the source end, right? Because you have, if your drain voltage is large, right, you have pinch off at the drain. Anyhow, intuitive arguments don't work. You really should work through the equations. A really good source to see the derivation of this charge partition is Savitas' book, which is a reference. So Savitas actually derives where this charge partition comes from based on current continuity equations. Another popular choice is the 50-50 partition. Half the charge goes to source, half goes to drain. You can see that practically there's not a whole lot of difference between these two. So you might as well pick the more physical charge partition. Okay? So the reason that SPICE can't actually tell you how charge distributes is because it's a lump circuit. The only way to actually figure this out is with a distributed model. And one way to do the simulation is to actually write a partial differential equation for the charge as a function of time and as a function of position, and to solve this partial differential equation. And this is done in this paper. Wegman and their co-authors. And it's an old paper, 1987, but it's a really interesting paper. I read through it this morning to remind myself. They actually set up the differential equation and solve it, and then they come up with a simplified normalized equation based on a simplified distributed model. And then they basically, the result of the paper is really just this graph. And so this graph kind of captures what happens to the charge Q1 and Q2. So let's look at the circuit. I draw the circuit here to remind ourselves. So this is C1. This is C2. This is our switch. And so this is C2 over C1. So based on how big these capacitors are, based on how quickly we turn off the switch. So this actually is kind of 1 over, actually this here is proportional to the fall time of the waveform. So this is T fall normalized to the omega T of the transistor. And so the idea is, first of all, just a couple of intuitive points on this graph. So this graph is the amount of charge going into Q2 versus the total charge, right? So if this is 1, that means all the charge is somehow going into this second capacitor. If it's 0, it's all the charge is going into this capacitor, right? And if it's 0.5, there's a 50-50 charge division. Now let's look at a couple points on this graph. If C1 is equal to C2, what would you expect? How should the charge divide? Okay, not a trick question. Shiji?
50-50.
Yeah, it's totally symmetric, right? Transistor is symmetric. The capacitors are equal. I turn off the channel. There's no reason for it not to be 50. If it were not 50-50, you would have to basically check into a hospital. Basically, you've gone crazy. Clearly, so there it's going to be, so for the ratio of 1, it should be right down the middle. Okay. Now what's interesting is you see on this graph, no matter what the ratio of C2 over C1 is, if the transition time is fast enough so that B is small, this B, let me just show you what B is. B is a normalized parameter. Let's zoom in and just look at B. So B is a normalized parameter. It has several terms in it, ratio of Cox to C2, the transition time, and a ratio of basically supply voltage divided by our V star. So this equation, what's really the most important parameter here is this part. How quickly we turn off our transistor. And first of all, why do you think it's normalized to omega t? Now this normalization wasn't chosen arbitrarily. It just drops out of the equations. But intuitively, why would this transition time have something to do with the omega t of the transistor? Yes.
I guess omega t means the time when you don't have current gain, so that the current goes to the capacitor other than.
Well, let's think of it more fundamentally. Fundamentally, what does omega t represent? Or better yet, what does 1 over omega t represent?
It's the time that the electron travels through the channel.
Exactly. It's sometimes called the transit time, because it's the time it takes for a minority carrier to cross the channel. So if we somehow turn off this transistor faster than omega t, there isn't even time for charge from one end of the transistor to go to the other end, right? So that's interesting. That's why omega t comes into play. So coming back to this graph here, for very, very fast transition times, we're over here. And it looks like all these curves kind of converge to 0.5. Does anybody have a good physical explanation why for very fast transitions we get 50-50 charge partition? It's kind of a subtle point. Not even sure if my explanation is quite good. But one way to look at it is that if you turn off the transistor almost instantaneously, then the source-drain junctions become pinched off together simultaneously. And once the source-drain junctions pinch off, right, because you can quickly pull charge away from the source-drain junctions, but if you're inside the transistor, there's not enough time to get charge out. So the only charge that leaves immediately is charge from the source-drain junction, and so they become pinched off. Once the source and drain are pinched off, the terminal impedances now don't matter. So no matter what capacitors you have, C1 and C2 here, this could be 100 times bigger than this, but these points are pinched off, so that if you're inside the transistor, you don't even see the effect of the outside world. And so then, again, it looks symmetric, and you get a 50-50 charge division. Okay? Now, if you have a slow charge, kind of a slow a very slow transition, so you're slowly turning off your transistor, then there's more than enough time for charges to flow back and forth. And in fact, you can imagine that the entire channel kind of equilibrates together. And so now the impedance that you have C1 or C2 matters, and charges will like to flow into the lower impedance node, right? And so for instance, if C1 is much, much bigger than C2, and we transition slow enough, we would expect all the charge to flow into C1. And this graph tells us if C1 is very large, then we're operating down here, and in fact this is the charge going into Q2, which is nearly zero. Okay? So this graph kind of makes intuitive sense. The extremes at least do. And then in the middle, you just have to solve differential equations to figure out what's going on. Okay? So based on this, here, yes?
Yeah, why the curves up and bottom that don't is kind of not symmetrical? It should be, right?
Why is the curve not?
The bottom curves and the top curves, they should be.
Why they're not symmetric?
Right.
It's a good question, because the values chosen here are almost symmetrical. Maybe because it's a log scale. I'm not sure. Yeah. Yeah, you have a good point. You would expect this to be symmetric. Yeah, my guess is it's the scale. No, actually over here it's a linear scale, so that doesn't work. Yeah, that's a good question. Don't have an answer for you. Okay, so based on this intuition, here is one solution to dealing with charge injection, and it's called the dummy switch. So the idea is you have this is your main switch, and then you insert this dummy switch. And you clock this dummy switch kind of symmetrically, anti-symmetrically. So when this is on, this is off, and vice versa. And let's say that I put two capacitors around my switch, my sampling capacitor, and then I reproduce a capacitor of equal size. Okay? Because now this is symmetric, what I'm hoping that happens is that when I turn this off, half the charge goes here and half the charge goes here. But at the same time, I'm turning on this switch, right? So this switch needs to get charge, and so some charge is going to flow into this switch. Okay? And let's say this is a high impedance node here, so no charge can come here. That means the entire channel charge for this switch has to come from this node. And so that could come from either this capacitor, or better yet, it could come from this switch. So if I can size this appropriately, which should equal exactly 1/2 the size of this switch, then because half the charge goes here and half the charge goes here, this half charge compensates this half charge, or this full charge, which is half, and so no net charge goes on the sampling capacitor. So this is one way to reduce the effects of charge injection, and here's some measurement results from back in the 80s. You can see that the amount of charge injection, which is of course signal dependent, is going from 40 millivolts up to 160 millivolts. With the dummy switch, it's cut down by, a lot, not quite an order of magnitude, maybe 3 or 4 times. And if you use the balance operation, so that actually you use a fully differential circuit, this is cut down even more. Okay? Now, why is it that you don't get perfect cancellation in this? Any guesses? Well, for one, the assumption here is that the situation is fully symmetric, right? That means that looking out here, you see the exact same thing as here. So if I look out here, I see a resistor and my signal source and a capacitor. If I look out here, I see a transistor and then a very high impedance, right? So it's not symmetric. And that's the reason you don't get very good symmetry. If you wanted to make it more symmetric, what could you do?
another dummy switch on the other side.
Yeah, you could do that. Another thing you could try to do is maybe make R very large, right? To kind of replicate what's going on this side, because you have a infinite input impedance. So if R is very large, then it becomes more symmetric, but of course that slows the circuit down. So, the whole point was you make this switch big, and so you have fast settling, and then you get charge injection, and then you make this R big to get rid of charge injection, and then slow again. So you've accomplished nothing. Okay, if we look at this curve again, we can also think of a few more ways of dealing with charge injection. So here are the different cases. One case is to actually operate very slow, extremely slow. So really slow fall time. And essentially, if we do that, then we're operating in this regime. And if we size the capacitors appropriately, we can make the charge injection very small. Okay? But of course, that means very large C1, which also slows our circuit down. So that's not very satisfactory. We just talked about this idea of a symmetric capacitor, C1 and C2. That means that we get the 50-50 partition, but again, we have this extra capacitor and this extra, and it's not perfectly symmetric. Another approach is actually to use a very, very fast transition. And that way you always get 50-50, regardless of what's happening, regardless of these matching conditions. So this scheme would work really well if you actually use a really fast transition, because then you would get 50-50. So that's one approach. Anybody think of another approach? Maybe number 4 here. Number 4, the idea is, well, we like using a parallel NMOS and PMOS switch already because that gives us a lower resistance switch over a larger range of voltages. And because these are driven in a complementary fashion, when this guy is turning on harder, this guy is tending to turn off, and so they can share some of their charge, and that would reduce the charge injection effects. Okay? Is that true? How well is that going to work? Well, I mean, it doesn't take a genius to figure out that NMOS devices and PMOS devices are not going to match very well, right? They have pretty different properties. They're fabricated in a different way. So to try to hope to get matching between an NMOS and a PMOS, it's not going to work. If you look at their curves, right, if you take a PMOS curve and you flip it around and you adjust the device size, they're not going to fall right on top of each other. And so what you're going to get is partial cancellation. So definitely it will reduce the amount of charge injection, but it will not be perfect. There's actually a bigger problem with using an NMOS and PMOS together, and that's the effects of basically, depending on the size of the input, the order in which these turn on and off is going to be different, right? So if your input is very low, then it's going to be really hard to turn off the NMOS, right? If the input is high, it's going to be hard to turn off the PMOS. So depending on our voltage, it's going to basically mean that the order in which the NMOS, depending on the magnitude of the input, the order in which the NMOS and PMOS turn off is different, and we end up getting what's called PM to AM conversion, because this takes the phase of our input, the amount that because the time when the switch turns off changes, that introduces jitter, and it's a jitter that depends on the input, and so it also generates distortion. And so, in fact, it turns out that if you're going to do this, you're better off using non-overlapping clocks. In other words, turn off the NMOS first, then turn off the PMOS. Don't try to do them together because you get this distortion. So how do we deal with charge injection? I mean, every solution that I presented to you, we've just shot down and said it's no good. Okay. So the solution actually turns out to be pretty simple. And the idea is can I convert my charge injection into an offset voltage? In other words, I want the charge injection to be independent of the input voltage. If I can do that, then I can get rid of the offset voltage with differential circuits. Okay. So here is how we're going to do it. So when these two switches are both on together, right, I take my input and I'm sampling it onto this capacitor, just like before, right? So I've introduced a new switch. So this is my original circuit. I introduce a switch here. Okay? And I'm going to actually turn these on both together, so they're on simultaneously, charge up this capacitor to my input, but now I'm going to use a different phase for these two clocks to turn them off. I'm going to actually first turn off this device. Okay? So this device will turn off first. Okay? Now we know that when you turn a switch off, you're going to get charge injection. Okay? Is this charge injection signal dependent? Will it vary with V in? Lee?
No,
How come?
because it's not connected to V.
Yeah, it's always operating at ground level, right? So when this switch is on, this node is practically close to ground, and so the charge is basically going to be a function of your common mode level. If this is not truly ground, some common mode level, but it's constant. So the amount of charge injected onto this capacitor when I turn this off is actually going to be it's going to be a constant independent of V in. Okay? And now if I had a second circuit, it would have the same input, basically the same error, and I could cancel out with differential operation. All right, then I turn off the second switch. And when I turn off the second switch, it also injects some charge into my circuit. Is this charge signal dependent? Obviously, right? I've got the input connected right here. Definitely. Because remember, the amount of inversion in this channel is a function of Vg minus Vt minus Vin. So Vin changes, this charge changes, and now some of this charge flows onto my circuit. It's a function of Vin, it introduces distortion. Does it actually deposit charge on C2? Vikas? You're sitting on the edge of the room to try to get away from questions, but it doesn't work. Can you use the mic?
Well, is this when the bottom transistor is off?
That's right. Yeah, we turn this one off first. It's a good observation.
So then wouldn't the charge coming from the bottom transistor go to C2?
It does, but that happened already. Now we're worried about the charge for this transistor B. So the question is, does the charge in the channel here deposit on this capacitor plate? Okay.
No, because the node is floating.
Right, exactly. So for charge to go onto here, for let's say this is an NMOS device, for negative charge to go onto this plate, corresponding positive charge would have to flow onto this plate. Where is that charge going to come from? Nowhere, because this node is floating, right? So that means that all of this charge has to go back into V in. So at phase 2, the charge injection doesn't actually enter our capacitor. So that's great. Phase 1, we have a signal-independent charge injection, and phase 2, we have no charge injection. Okay, so that the problem is solved. Here is one implementation of a sample and hold, also called a track and hold amplifier. The reason this is called a track and hold, so one small distinction between sample and hold will just sample your signal and hold it at one instant. Track and hold will track the input and then hold the value when you tell it to. One small distinction. So here, I'm going to use this technique. This is my sampling capacitor. Now it's fully differential, and so I apply my input during phase 1. These switches are closed. This switch is open, right? And I short out my input of my amplifier. And what happens is, basically, forget about the amplifier. The amplifier just presents some input impedance here, and if it's a good amplifier, it presents infinite input impedance. And so this circuit in phase 1 is identical to what we just looked at. I would basically sample half my differential voltage here, Vin over 2, right? And the other half gets sampled over here. So this would be minus Vin over 2. So the input gets sampled across these two capacitors differentially. And then I turn off these two switches, right? And that produces charge injection. But because both of these switches are operating at the same common mode voltage, their charge injection is equal and constant, right? Then in phase 2, I turn off these switches, so I disconnect the input. I disconnect this common mode voltage from the input. And now I connect this capacitor to the output. So what happens? Now, at the output, I have Vn over 2 plus some offset, right? Plus some charge injection, let's say, minus Vn over 2 minus the offset. So clearly the offset cancels out. So the charge injection produces an offset which cancels out. If you look at this amplifier, it's interesting, this track and hold. This amplifier is actually not doing much, because on the second phase, the input gets transferred to the output through these capacitors. The actual amplifier doesn't even need to change its output. The output's already at the right value, right? And that means that we just have to design this transconductor to deliver, basically transfer this voltage to the load. So any extra charge to charge up the load to this basically input level is provided by the amplifier. Okay? Questions or comments about this? Yes.
Question. A couple lectures ago, you introduced a method where you have a constant VGS across MOSFET, bootstrap, and so on. For those type of methods, you still need bottom plate sampling for injection cancellation?
So if you do constant VGS sampling, then again your charge injection is going to become a constant. And if you use differential, you can get rid of it. But remember, it varied with the body voltage, right? Because so if you want to use these techniques together, you get even better performance. Okay. Couple things about this. What's the gain of this track and hold? Well, it's 1, because we just take our input and then swing it around and put it at the output with these capacitors. So this circuit always has a gain of 1. So if you wanted to get higher gain, you'd have to use some somewhat different technique. The other interesting thing is that this circuit uses a feedback factor of 1. So it has to be unity gain stable. That's because ideally there is no capacitance sitting here, right? Ideally. So the feedback factor, which is this capacitor divided by this plus this capacitor 0, is just 1. in fact, there's always going to be capacitance here, right? And so, in reality, feedback factor is not quite 1, it's a little bit less than 1. What about the error introduced by this capacitor? Is that an issue? Remember, my assumption was that when I turn off this switch, no charge can go here because this node is floating. Well, now I've got an extra capacitor sitting at that node. So what's going to happen? Will this node just stay at the same potential? No, because it's a capacitor divider, right? So if this node moves, then this node will also move. And so this capacitor actually introduces a new source of error. But this circuit takes care of it, because when I then put this capacitor in feedback, the amplifier forces basically these two nodes to be equal, right? So this becomes a short, and so it automatically discharges this capacitor back to the right value. So any parasitic capacitance at this node doesn't hurt us. And of course, you know you're going to have parasitic capacitance at this node. The gate capacitance of this transconductor, the drain to bulk capacitance of the switch, and so on. Okay? There is one small problem with this circuit, and the problem is that the entire common mode at the input, so if I had, this is a pure differential input, if I had common mode, so if I add common mode voltage to both sides, then that common mode voltage also gets sampled onto these capacitors and then transferred to the output. Okay, so that's one disadvantage of this circuit. Let's look at a different track and hold. It's actually just a switch capacitor gain stage. If you think about it, this is the circuit that you guys have been working on. It's also a sample and hold, right? It samples your input and it holds it. So why not use this? It has gain, right? It doesn't have to be a gain of 1. And if I design it right, I can also reject the common mode at the input. So if we look at this, you guys are pretty familiar with this, how this works now. In phase 1, I have these CMOS switches, and I ground this point. So this charges the input to the right value. So during phase 1, this is a short, this is a short, this is a short. This, of course, discharges this feedback capacitor. This takes the output to some known level, common mode level or ground or whatever. And this, during this phase 1, I charge these common mode capacitors to the right voltage. Phase 2, I connect them back up again. And you know that in a few cycles, this circuit would force the amplifier to have the right common mode level. So now, all I have to do is be careful that in phase 2, I turn off this switch slightly before this switch, right? Because if I turn this switch off first, its charge injection will go on to here as a common mode signal. And then when I turn off this switch, it can't inject the circuit current here because this is floating. This capacitor is now floating. And now you'll notice that in phase 2, what I do is I short this out. I now have feedback around my amplifier. And now you know that the charge of these capacitors get transferred onto these capacitors, right? Because I'm discharging these capacitors by the action of the op-amp, assuming infinite loop gain, And so that you get the charge transfer, and then the voltage gets transferred to the output. And by having a ratioed capacitor, you guys know that I can make gain. So here I have a gain of 4, for instance. And by also shorting the input as follows, I get rid of the common mode at the input. So now the common mode here and here cancel out, right? I could have alternatively just grounded both inputs and not had the switch. Circuit still would have worked, right? That would have forced the charge transfer here and here. But that would also transfer the common mode from the input to the output. Now with this switch, I short out the common mode. Basically, I have plus common mode, minus common mode, so they cancel out. And this also rejects the common mode. Okay, questions? All right. So one last thing to consider with sample and holds is jitter. And the way to think about jitter is basically you never have a perfect clock, right? Say this is a perfect clock. If you look at a real clock, then there's always variation in the transition time. So maybe you transition early, maybe you transition late, so there's going to be some jitter about the ideal transition time. And if you look at more and more waveforms, eventually this transition kind of becomes fuzzy, right? The actual transition time varies statistically. So that means that we actually don't know when we're going to sample our input. You think you're sampling it every nanosecond, but it's every nanosecond plus maybe 100 plus minus 100 picoseconds, where that is your standard deviation. So this clock skew, we like to see what this clock skew does to the accuracy of our sample and hold. And just to give you some ideas, if you build a clock and you're not very careful, you can easily end up with 100 picoseconds of jitter. 100 picoseconds RMS. If you do a really good job, you hire an expert PLL designer and they come in and spend 6 months, they can get the jitter down to less than a picosecond. Okay? So why is this jitter important? Also, where does this jitter come from? Well, even if you had a perfect power supply, right? So everything is perfectly grounded, you still observe jitter. And that's due to just the thermal noise in your transistor. The thermal noise in the transistor causes the transition time to vary. But often, you're actually not dominated by that. You're dominated by something as simple as the noisy supply voltage, right? Because if this supply voltage varies, then the transition point of these inverters varies, and that means that we introduce jitter to the output. So we come in here with a perfect clock, and we vary VDD, and now the output has jitter. Okay. So again, you spend $500,000 and design this jitter-free clock, but you forget about the power supply, you're dead. And just to give you an idea of how important this is, in this example, let's say that this inverter has a delay of 100 picoseconds, and the delay varies 20% per volt change in the power supply. 20 picosecond per volt change. So that means that if you had 200 millivolts of jitter, 200 millivolts of noise on your power supply, multiplying 200 millivolts times 20 picoseconds introduces 4 picoseconds of jitter into the output. Okay. And the way that jitter introduces, so that's jitter. You're going to live with it. It's either going to be 1 picosecond or 100 picoseconds. At the end of the day, how does that impact the accuracy of our sample and hold? Well, if this is our nominal sampling time, if this is our input waveform and it's varying, and we intended to sample it at this point, but unfortunately because of jitter, we end up sampling it at this point. So how much error does that introduce? Well, if this time interval is very short, which is a good assumption for jitter, then we can just do a linear expansion, right? We could say, well, the error is approximately, if I take the slope here and multiply it by the time interval, that is the error due to the sampling jitter. And obviously, if the signal doesn't change in that interval, there is no error. So this only matters for AC signals. And the faster the signal varies, in other words, the more high frequency content it has, the more error we introduce because of jitter. Okay. So putting down an equation for what we just said, this error amplitude, E, is just the time difference, this delta t, times the derivative of our waveform. Okay. Now, surprisingly, if you just plug this into a simple case, let's just assume our input is a sinusoid, right? That's a good assumption, because we know whatever the input looks like, I can always Fourier decompose it into a bunch of sinusoids. Then the highest frequency component in our sinusoid is going to give rise to the largest error, right? Because that's going to have the biggest slope. The slope of a sinusoid, of course, is also a delayed sinusoid, and if you get lucky, the slope is 0, right? If you catch the peaks. If you get unlucky, you get it at the transition point of the sine, and then the error is actually, the slope is actually the magnitude. And so the largest value of the slope is going to be 2 pi fx, where fx is the frequency of the sinusoid, times a, the amplitude of the input. Okay? And so now if I take this error and multiply it by delta t, I can calculate effectively how large this error is in terms of, I can basically quantify this error. I want to say the error should be much less than half an LSB. So my LSB is the full scale amplitude divided by 2 to the b plus 1, because I'm taking half. And so then the worst case scenario would be a sinusoid which is at the highest possible frequency, fs over 2, with the highest possible amplitude, full scale amplitude. Plugging in the numbers, this tells me how much jitter I can tolerate for a given basically frequency and certain resolution. So let's start over here, 16 bits. That's pretty reasonable. I want to design a 16-bit precision sampler, and I'm going to sample at 10 megahertz. That translates into half a picosecond of jitter. You cannot tolerate more than half a picosecond of jitter. Wow, just 10 megahertz is not fast, right? But because there's so much resolution, just a little bit of error is bigger than your LSB. So you might say, okay, I'm going to back off. Let me back off to 12 bits. Let me back off to 12 bits and 100 megahertz. Think about like a system like wireless LAN. If your IF, if you sample it around 100 megahertz, right, because it's a relatively wideband system with 12 bits of resolution, you can it's probably enough, more than enough resolution to do lots of signal processing on the baseband side. But you still require less than a picosecond of jitter. Okay? So really interesting, if you want to sample directly at RF, right? A lot of people say, forget building a radio. Just put an A to D converter right at the antenna. And boy, forget all this complicated analog RF circuits. Even for 8 bits at a gigahertz sampling, you need at least a picosecond of jitter. And you know what? 8 bits is not going to cut it. 8 bits is not that much resolution. If you want to build a so-called software-defined radio, you're looking at more like 12 bits. Actually, more than 12 bits. You need about 100 dB of dynamic range. And remember, it's 6 dB per bit. So you're basically, even 12 bits is not going to do it. So even if you could build this A to D converter with a reasonable power consumption, you just can't clock it. Because the moment you clock it, you introduce error. All right. Questions or comments about this? All right. So now I'm going to go through next topic, and we have about 30 minutes for the next topic. The slides are all online, so if I go through quickly and you're interested in more details, I urge you to look at the slides online. or to read the references that are quoted. Okay, the next topic is offset cancellation, and just to give you, a sense for how important this is, offset cancellation saved your butts in the project. Because if you didn't have offset cancellation, you would have had to deal with flicker noise. But we just assumed that we could get rid of the offset with the flicker noise with an offset cancellation circuitry. Okay, so you guys should all thank people who invented offset cancellation. Okay, so offset cancellation, the few different techniques. We're going to talk about correlated double sampling, which is a technique to reduce the low frequency offsets in our signal. We're going to also talk about chopper stabilization. We've actually talked parenthetically about both topics. There's a good paper here by Ance and Temis that discusses various techniques for reducing offsets in op-amps, and it's in the proceedings of the IEEE. And if you've never read one of these papers, I urge you to go look at some of these, because the papers in the proceedings tend to be, instead of being cutting edge, they tend to be more review papers, or almost like tutorial, state-of-the-art papers. So you can read this paper and get an idea for all the different techniques that are out there for reducing offset voltages. Okay, one simple technique to get rid of offsets is something we looked at even before. We looked at input offset cancellation before. This is actually a variation on that. It's called output offset cancellation. And the idea is as follows. If you have a switch, kind of a switch capacitor system, you have time intervals where you could try to get rid of things, get rid of bad things. So during the time interval where the amplifier is not working, why not try to measure its offset voltage, and then in the next cycle try to subtract that offset voltage from the input. And so here we can see that what we do is, in the cycle that we don't need the amplifier, we connect its positive terminal to ground, and its inverting terminal, basically we also ground, which means that the amplifier output is going to be the gain, the minus the gain times the offset voltage, right? So if this amplifier has a lot of gain, what happens? Well, either clamp to the positive supply or the negative supply, right? Because we don't know the sign of the offset. We just, we can estimate its kind of its RMS value. So if there's too much gain, this circuit is useless. It's just going to store either plus VDD or minus VDD on this cap. If, on the other hand, the gain is not so large, then, and the output doesn't clamp, then we can do something useful. So this technique will only work for relatively small gains. So if your offset voltage is 10 millivolts, right, gain of 20, okay, that's 200 millivolts, that's fine. Gain of 50, maybe 500 millivolts, that's fine. But a gain of 10,000, right, forget it. It's not going to work. But as you can see here, during the first phase, the output capacitor is going to get charged to a value Vc, which is minus A times the offset voltage. And it's negative, of course, because we just assume the offset's at the negative terminal. I could have put it at the positive terminal, right? It doesn't make a difference at the end of the day. It better not, otherwise the technique's not going to work. Now during phase 2, I hook up my input to the amplifier and basically take the output here. So the output is now A times the input voltage. The input voltage is Vin minus the offset voltage. So this is A Vin minus the offset voltage. But then the output voltage is actually lower by this capacitor voltage. And I charged up the capacitor voltage to minus AV offset. And so clearly you can see now that the minus Vc here term cancels with this term, and the output is just a magnified part of the input. And any offset voltage has been canceled out. Okay? Very simple idea. If this offset voltage were kind of low frequency noise, like 1/f noise, then because 1/f noise, right, peaks at low frequencies, most of the energy is in fact at low frequencies, close to DC. So if this auto-zeroing technique, if I switch from one state to another at a rate much faster than where the noise is, then clearly I'm going to reject that noise. Because from one cycle to the next, the offset voltage, which has a flicker noise component in it, has changed hardly at all. And so the low frequency part of that flicker noise is going to get eliminated. We'll quantify that in a moment. Okay, so what if you have more gain, right? You're building an op amp. You have a gain of 10,000. Well, you can still use this technique if you do offset cancellation stage by stage. So if you break up your amplifier into multiple stages, then you can obviously take away the offset of each substage, and the overall amplifier will not have an offset voltage. Well, there's actually a clever way of doing this. Instead of basically turning all these switches on together and then turning them all off together, there's actually a good way of turning these on and off. Anybody guess why? What can we gain by using timing to our advantage? Well, what happens when we turn switches off? You get charge injection, right? So is there an order in which I could turn off these switches to minimize the charge injection? Okay, well, let's look at this proposed timing diagram. So this timing diagram is telling me that I should first have switches 2, 3, and 4 on. So all of these are on. And switch 1 is switch 4. Okay, so 2, 3, 4 are on at this point, and switch 1 is off. Okay, so stage 1, this is what I have. And that means that this capacitor gets charged to, right, the offset voltage times the gain, just like before. This capacitor gets charged to this offset voltage times the gain. Okay, that's exactly what we want. Now, as we go, this is hard for you guys to read, but you can look at it. The proposal now is to turn off switch 3 first. Okay, so I turn off switch 3. And that creates some charge injection, right? So that will basically put some charge onto this capacitor. All right. Next, the proposal is to switch number 4. So number 4 goes open, and this also introduces some charge injection. And then finally, at the very end, I'm going to open up this switch and connect the input. So the idea is that I'm taking the charge injection of these switches and making them into constant offset voltages, which I can cancel out, right? In fact, it doesn't even matter that they're constant. Here they turn out to be constant because I've shorted this to ground. But by doing this in the right order, I put basically an offset voltage here. I increase, in effect, it looks like I've increased the offset voltage of this guy, but I can cancel it out with this capacitor. And so timing this appropriately can really greatly reduce the offset voltage. There is one problem, though. The problem is that the last device's offset voltage is not canceled out, right? But that's okay, because the offset voltage of the last stage referred to the input is tiny. It's really the first few stages that dominate the offset voltage. So this paper describes this technique, and you can see here that they've some statistical measurements. Their offset voltage is reduced, the standard deviation, less than 5 microvolts. So this is a differential implementation. It also uses chopper stabilization, which we'll talk about later. Okay, so that is output offset cancellation. Another technique is input offset cancellation, and we actually looked at input offset cancellation a few lectures ago. The idea is, if I have lots of gain, if I try to do output offset cancellation, I'm going to rail my amplifier, right? So instead, what I do is, in one phase, I'm going to connect this capacitor basically on the input, and this capacitor I'm going to short, so the amplifier goes into unity gain configuration. So because it's in unity gain configuration, this node has to equal this node, which means that this capacitor charges up to my offset voltage, right? Assuming infinite gain, infinite loop gain. Now in the next stage, I'm going to operate my amplifier open loop. I open this switch, and I connect the input here to the actual input of the amplifier. Now the input of the amplifier is the offset voltage, the input minus the offset voltage. And so I actually cancel the offset voltage. Okay. If you do this calculation a little bit more carefully and assume you have a finite amount of gain, you can do the math. It's pretty trivial. At the end of the day, you do end up with a residual offset voltage. And the residual offset voltage is basically the offset voltage you started with divided by the gain of the amplifier. Great. So if I have a gain of a million, right, forget the offset voltage. Even a gain of a few thousand, I start out with 10 millivolt offset, I'm down to microvolts, tens of microvolts. So this is a great technique. What can anyone think of a disadvantage of this technique? There's no reason why I actually operated my amplifier open loop in the second phase, right? What if this were a feedback amplifier? In that case, I could have even used this capacitor, which is part of the feedback network, to store that offset voltage, right? Anyone think of a disadvantage of this approach? Well, the disadvantage is that in phase one, I operate my amplifier unity gain, which means for compensation, even if in closed loop I'm going to operate with a gain of 5 or 6, I still have to compensate it for unity gain, which is the worst case, right? So I end up overcompensating the amplifier just because of this requirement that it has to be stable for unity gain feedback. Okay. Here's the idea. If you're using a switch capacitor circuit, you can play the same exact trick. In phase one, I close my switch, right? This is in unity gain. And then this capacitor here, it's charged up to the offset voltage plus the input, right? So in phase one, I charge up this capacitor to Vin minus VOS, because this is in unity gain configuration. So this cap now holds input plus my offset voltage. And then in phase two, I connect this to ground, right? And that flips the offset voltage polarity, which now cancels out here. And this is exactly what I was talking about, that in phase two, we're going to actually operate this as a switch capacitor gain block. But in phase one, because we had it in unity gain, we end up having to compensate it that way. Here's a little bit more detail on this. I'll let you guys go through it on your own. It's just breaking down the circuit in phase one and phase two. But I think you've seen this circuit enough that you don't have to draw it separately. Here's a technique that actually is meant to reduce the glitches in this amplifier. Um, because our clocks are non-overlapping, there's actually going to be a time in which the amplifier is operating open loop. And because the amplifier is operating open loop and has lots of gain, it could very easily rail, right, to positive or negative supply. Which means that in cycle 2, we've got to unrail it, which means slew rate limiting, right? So here we introduce an extra capacitor, Cx, which always provides some loop gain for our amplifier. So even when on the non-overlapping clock, when these switches are all off, there's still a feedback path to prevent our amplifier from railing. Okay, I want to kind of skip ahead a little bit. One technique that I'll just refer to here and let you guys look at the slides. Completely different approach. So we looked at output offset cancellation, input offset cancellation. Another approach is the so-called auxiliary amplifier offset cancellation technique. And the idea is that you embed two amplifiers into your amplifier. How do you do that? Well, here's an example. You guys recognize this simple amplifier. Here's my input diff pair. This is their current source. And then I have a mirror to the output. So this is the first mirror, this is the second mirror, fully differential. And in single-ended operation, I can mirror this current back, and this is my output node. So the gain of this circuit is the GM times the output impedance, right? Here I introduce the second diff pair, two separate input terminals to ground, and I take its current and also mirror it to the output. So this is two amplifiers kind of in parallel connected to the same output. So maybe you would draw this perhaps like this. There's two inputs, one output. This is my primary input, this is my auxiliary input. And the idea is that my auxiliary amplifier is not going to have as much gain as my primary amplifier. So if I had such an amplifier, so this amplifier actually has, this is a single-ended version, so this is the main input, this is the auxiliary input here. Okay? So if I go through and analyze this circuit here, you'll see that at any given time the output is the gain of the main amplifier times its input voltage and its offset voltage minus or plus really the gain of the second amplifier, the auxiliary amplifier, plus the input minus its offset. Clearly it's going to have its own offset voltage, which is different from the offset of the main amplifier. And if I analyze this circuit, again I apologize, we're going to go a little bit fast, but at the end of the day I find out that the output of this circuit as a function of the offset voltages has the following form. It has the offset voltage of the first amplifier divided by A2, the gain of the auxiliary amplifier, the offset of the second amplifier divided by the ratio, effectively if A2 is large, the ratio of A2 over A1, and then the normal gain operation. So what you see is that very simply, the simplest thing is just to make A1 very large. If I made A1 very large, then the offset of the first amplifier is rejected by A2. In fact, A1 should be much larger than A2 is what we need. And then the offset of the second amplifier, the auxiliary amplifier, is rejected by this ratio of A2 over A1. So, of course, we skip the details here. I encourage you guys to go through that if you're interested. And there's a couple of different references. Here's an amplifier using this technique. Again, a Berkeley paper from Paul Gray's group. Let's skip ahead a little bit. Okay. So the question is, how does this idea of auto-zeroing, one way to look at it is that what we do is, in one cycle, we sample our offset voltage here, and we hold that. So somehow it goes into some kind of sample and hold circuit. And then on the next cycle, we connect this to our input, and we subtract our input from the sampled value, right? So hopefully this input has our offset voltage and it's roughly the same, and so when we subtract them, our output is just the input voltage and the offsets cancel out. Okay? So this is a block diagram for effectively what we've been doing in all these circuits, is somehow holding the offset voltage in one cycle, and then the next cycle measuring the input with the offset and canceling it out. In terms of equations, that tells me that the output at any given time is the gain of the circuit, which may be 1, times the input voltage at time, let's say k, if we're talking about discrete time, at time kt, if you like, plus the offset voltage at that time, minus the offset voltage that I had stored 1/2 cycle before. So kt minus t over 2. Right? So this is really a time equation that tells me how the statistics of the offset voltage are going to change. So I take the sample at one time and subtract the sample half a time before. If I take a difference in the time domain, what does that look like in the frequency domain? It's intuitively, right? What operator does that look like in the frequency domain? No, just intuitively, right? If I take the difference between two samples with a fixed time interval, that's like taking the derivative of the input, right? And what's the spectrum of the derivative, right? 0 at low frequency, right? But very high at high frequencies. So in effect, what I'm doing is I'm multiplying my noise by a transfer function that rejects the low frequency portions, but actually amplifies the high frequency portions. So you have to be careful. We're actually going to amplify the noise, but we're going to amplify the good noise, which is the small noise. Okay? Well, you can also do this mathematically. This operation, of course, in the Laplace domain is a delay, which corresponds to multiplying by an exponential. And so the transfer function for this operation is the output is the transfer function of the offset voltage is the output offset voltage is the input offset voltage multiplied by 1 minus e to the minus st over 2. Okay? And we can very quickly calculate what this is in the frequency domain. We just plug in j omega here and use Euler relation for exponential, so that's cosine plus j sine, right? And let's say I'm interested in the magnitude response, so I take real part and imaginary part squared. That's done here. And a couple lines of simple trigonometry, and at the end of the day, the transfer function looks like a sine function in the frequency domain. And that kind of jives with our intuition. It's saying the transfer function at very low frequencies is attenuating the noise, and at increasingly higher frequencies, it's actually amplifying the noise. Here's a plot of that transfer function. This is the transfer function. Let me make sure it's the right plot. This is here the transfer function squared. That's why it has this little curvature here. And this is normalized to Fs. So this is the noise appearing at the sampling frequency. So if the noise is much, much lower than our sampling frequency, then it's going to be practically attenuated. And this is a plot of the product of our noise spectrum, which is like 1 over f, times this transfer function, and you get this curve. Okay? Remember, originally this curve was like this, so what we've done is we've really attenuated the low frequency parts of the noise. So not just 1 over f noise, but any kind of noise. Even thermal noise at low frequency is getting attenuated. Okay? What are some of the disadvantages of this system? Well, if you've studied discrete time systems, you know that anything appearing above your sampling frequency actually aliases back on into your band, right? And so high frequency noise above your sampling frequency is actually going to alias back down into your band. So all the noise from the higher frequencies is also going to appear. That's why we get KT over C noise from the thermal noise, right? But now all that noise that we actually amplified is also going to alias back onto us. But of course, as far as 1 over F noise goes, above the corner frequency, the thermal noise dominates. So if the corner frequency is below our sampling frequency, that means the folded noise is essentially going to be KT over C. Make sense? Okay, good. Another technique for dealing with offset voltages is called chopper stabilization. And we also talked about this we took a little detour and talked about this a while back. And the idea is, again, pretty straightforward. What we're going to do is we're going to take our input signal and chop it up to a higher frequency. By chop, I mean use a mixer. And you can think of it, we're going to multiply it by plus or minus 1 at some high frequency. Let's say 10 kilohertz. At this higher frequency, the noise basically, let's say 10 kilohertz happens to be above our 1 over F noise corner frequency. So at this higher frequency, the 1 over F noise is essentially negligible compared to the thermal noise. So then we amplify our signal, which is now a bandpass signal. It's centered at a kilohertz or 10 kilohertz, whatever the chopping frequency is. And of course, it really appeared it's a low frequency signal to begin with, so we really have to down convert it. So now we down convert our signal back to baseband. So we have two mixers back to back, and the net operation is as if the mixers weren't even there. Effectively, what we've done is the second mixer chops up the noise, right? Because at the output here, we have the input noise gained up, but also chopped. By chopped, I mean mixed. And so what this circuit does is it moves the noise to a high frequency and keeps the signal at the baseband. So here's a spectrum. At this point here, you can see the signal is basically translated to a higher frequency, frequency translated. Why do I get these terms? Anybody? Christian?
The higher order harmonics present in the square wave, for that you can chop the signal.
Exactly. I'm chopping it here with a square wave, and so basically I can predict very simple math that I'm going to frequency translate the signal up to, let's say, the chopping rate, and then because this is an odd waveform, I'm going to get, let's say, the third harmonic here, and I'm going to get roughly 1/3 the amplitude on the third harmonic, and and so on. The noise at this point is actually low frequency. At this point, I down convert my signal, so now it's again a baseband signal, but the noise has been up converted. And so if I low pass filter, I can preserve my signal and get rid of the noise. So very simple concept. A couple of small wrinkles. Wrinkle number 1. The amplifier basically has to be broadband, right? Because if it's a narrowband amplifier, what's going to happen? If it doesn't have enough bandwidth, I'm only going to gain up, let's say, the first component that was chopped. The third and fifth harmonic will get attenuated. If those are attenuated, when I then down convert back down to baseband, the overall gain of the amplifier shrinks because I lost some of the energy of the signal. And if you do a simple calculation, let's say the bandwidth of the amplifier happens to be twice the chopping rate. That means I lose my third harmonic, my fifth harmonic, and so on. The effective gain drops to about 0.8 in that case. Okay? So that's one disadvantage. The other thing is that the amplifier should not introduce any phase shift into the signal. Because worst case scenario, let's say the amplifier introduces 90 degrees phase shift at some frequency. Then the first chopper chops me up with 0 phase shift. I go through 90 degree phase shift. Then the second chopper, instead of being in phase, is actually in phase quadrature, which means the output is going to be 0. So the frequency components that experience 90 degree phase shift have a gain of 0, effectively. So again, I really need my amplifier to have good bandwidth and to have very low phase shift. If I can do that, I can get really good performance. So this is from a paper, Paul Gray and Messerschmitt, names you'll recognize. And this is showing you the noise, the measured noise, basically I believe this is the output noise, with and without the chopper. So without the chopper, you see the 1 over f noise spectrum. And after you chop this noise, let's say at 16 kilohertz, this is what the noise looks like. And if I chop it at a sufficiently high frequency, right, way above the 1 over f corner of the noise, which appears to be around 30 kilohertz, then the noise is almost eliminated, right? You don't really see the 1 over f noise now. It just looks like thermal noise. So clearly, this technique works. You need a filter, though, right? The circuit won't work unless you have a filter. I'll let you guys look at this paper on your own. Actually, if you have a good idea, do it again, right? So this is a nested chopper. And the idea is, if you chop too fast, you introduce glitches. So why not chop fast, make those glitches appear like an offset voltage, and then chop slow to get rid of those. So I'll let you guys look at that, and you get some pretty good results. So here's a very last slide here is a comparison of these two techniques, the correlated double sampling versus chopper stabilization. The advantages and disadvantages, of course, you have to have a sampled system for correlated double sampling. For a chopper, it can work with a continuous time signal. Both of them reduce the flicker noise. One needs a filter to get rid of it, though. So the chopper needs a filter to actually eliminate that. Okay, that wraps up the lecture. Thanks, guys.